Okay, so what we're going to do today is continue our discussion a bit more about stationary sets. I don't know if anyone wants to ask me about that. I'll review the definition again, of course, before we continue. And I'll do a couple of those exercises that I just drew your attention to. Okay, let's go. So recall then a stationary set contained in omega, where omega was a regular cardinal. So this is a set that hits all closed unbounded sets. So it has non-empty intersection with every C contained in omega, which is CUB. So if we think of these as C as being thick, S is sort of like semi-thick. Right? Whereas this contains all of its limit points. S needn't contain all of its limit points. In S. It will have to contain some of its limit points in order to be stationary, but it needn't contain all of its limit points. Right, so where did those exercises go? So 212. So that just said I've got S that's stationary and C that's CUB, and this is CUB. Then S intersect C is stationary. So it's not just that a stationary set has non-empty intersection with C. The intersection with C is also semi-thick. So S intersect S hits C in many places. And it's a one-liner, really. What does it mean to be stationary? It means you intersect every CUB set. S intersect C, intersect D to be non-empty. That's what it means for this to be stationary. Take an arbitrary CUB set, non-empty intersection. But this is just S intersect C intersect D. Right, intersections associative. The intersection of two CUB sets is CUB, as we've seen. But S just alone is stationary. So this is non-empty. So all we do is just shift the brackets over and appeal to the fact that S is stationary. Okay, any queries? Um, 213. So again, I've got a stationary subset of omega here. Show that S intersect S star is stationary. Well, that's just two observations. Solution. S star is CUB in omega. It's unbounded in omega because S was unbounded in omega, and S star is the collection of closure points of S. So it's closed. And indeed, there's this is exercise 2.6. So let's recall. EV contained in omega is any unbounded set. It doesn't have to be stationary. Then E star is CUB in omega. Okay, so we don't actually have to write that bit out. It's just enough. You can just say straight off, S star is CUB. But now all I've got is S intersect a CUB set, and the previous exercise says that that's stationary. Right? I'm just plugging in S star here in the previous exercise. So by the previous exercise, S intersect S star is stationary. Right? So all you have to say is this, and then this, and then you're done. Right? So those are some basic properties of stationary sets, as are 214 and 215 coming up. We'll finish our discussion of stationary sets with Fodor's lemma, which is 219. It's on page 23. And that's as far as we'll go. So let's see what Fodor's lemma says. So this is a basic property of stationary sets. So what is the setup? The setup is we've got a function that's so-called regressive on a stationary set. So this is called Fodor's lemma. Fodor proved in the 50s a sort of preliminary version. No, sorry, I'm misspeaking. I'm jumping ahead of myself. So I'll stick with the notation in the notes. For some reason, I've taken kappa rather than omega. So since I'm emphasizing it's a regular cardinal here. Then the following are equivalent. A set is stationary in kappa and any function that's pressing down, or we say regressive on S, So any function whatsoever. And the property that it has is you pick any alpha in S, at least if it's non-zero, then it's pressing down or it's regressive. Anyway, f of alpha is always less than alpha. So the picture is, here's kappa, here's S. So what f does is just push ordinals downwards. And the equivalence is fulfilled if whenever you've got a regressive function like this, then there's a stationary subset of S and a fixed alpha 0 so that actually all of these points on S0 are going down to this one point, alpha 0. So that for all psi in S0, f of psi is alpha 0. So it's not just that it's pressing down, it's constant on a semi-thick subset of this semi-thick set. So again, in particular, if C is a closed unbounded set, if F is pressing down on a closed unbounded set, it's sending stationary collection of points to one point. So it's constant. I'm tempted to say almost everywhere. It's constant on a semi-thick set. Okay, so I hope that's clear. If anyone wants to ask anything about the setup. Notice that 2 implies 1. We said this is equivalent. 2 implies 1 is kind of trivial. Because we've got a function on this S here, but 2 says there's a stationary subset of S. Well, if S contains a stationary subset, S is stationary itself. That if, let's choose different letters, if U is contained in V, here contained in kappa, and U is stationary, then V is stationary. Why? Because if U intersects any CUV set, obviously V intersects any CUV set. So I'm not going to write that out. So 2 implies 1 because 2 says S has got a stationary subset. So obviously S is stationary. We don't have to say anything else there. So it's the other way around. It's the content of the lemma here. So we assume S is stationary. In kappa here. Now suppose 2 failed, right, for a contradiction. So there'd be some function such that this, which didn't have these properties. So we assume 1 and see what happens when 2 is assumed to fail. So if 2 failed for some regressive function f, then what will be happening? what we do, we'd be able to define, I'll define sets y sub alpha here. And this will be the collection of psi. So it's that psi is in S and f of psi here is not alpha. So I mean, we need to think about it a bit. We've got this regressive function, supposedly, right? And it's not constant on any stationary subset of S. So we look at those psi's in S where f of psi is not alpha, right? And I'll call this alpha. And this is for any alpha less than kappa. So if the conclusion fails, it's saying that this is not a stationary set, right? Because a collection of elements of S which do go to, sorry, which is alpha. I'm sorry. We look at the things that do go to alpha. This is not stationary because that's what the failure of 2 says. So if 2 is failing for this F, each of these Y alphas is not stationary. But what is it to be not stationary? Well, it means there's a CUB set which you don't intersect. So there's a CUB set C alpha contained in kappa, witnessing that Y alpha is not stationary. That's what it means for Y alpha not to be stationary. So what have I got? I've defined a kappa long sequence of CUB sets. So now I can deploy that definition of diagonal intersection here. So let D be those alpha such that for all beta less than alpha, alpha is in C beta. So I've got this sequence here of sets, and the diagonal intersection, as from before, it's those elements that are in all the previously indexed sets. Then D is CUB in kappa. Right? A diagonal intersection of CUB sets is CUB. Okay, so now I've got a CUB set, D, this sort of quasi-intersection of all the C betas. Okay. Our original S, we assumed, is stationary. So S intersect D is non-empty. So let Tor be in D intersect S. Okay, Tor exists as S is stationary. Okay, now we're getting to a contradiction. So we ask, what does F do to Tor? Well, f of tau, it's a pressing down function on elements of S, so it sends it to something lower than tau, right here. So it's some zeta or other. So let zeta equal f of tau. But now, what is the contradiction? Zeta here, right, is in C tau. Sorry, other way around. Tau here is in C zeta. Tau is in the diagonal intersection. So it's in all of the previously indexed sets. So zeta is less than tau, so tau is in C zeta. Right? But then what is C zeta? It avoids this Y zeta. And what does this mean? If it's not in Y zeta, we can't have here that f of tau is zeta. Sorry. It's not zeta. So this is the contradiction. We named f of tau here as this zeta, but in fact, we deduce that it's not this zeta because of this diagonal intersection property. So this is a contradiction. So our supposition that 2 failed here was wrong. Right? 2 must hold. Okay, that's a little. You will probably want to, read this through another time. I mean, this is a little. Just this last maneuver just looks a little bit like magic, right? This last thing here. But all we're doing is chasing the consequences of our definitions in our setup. That's here. Anybody want to ask anything? Right. Okay. Now the rest of this page and the next theorem and the next exercise, the rest of this page you can omit, right? Won't be part of the course. So let's say we'll omit we'll omit 690 to 715. Okay, so please take a note of that. Again, I'll put this up on the web page on the course site, but anyway, be giving you a list of the things that we omit. Yeah. We're also going to omit the next section. I believe I already said that, or put that up on the, again, on the course site. So we're also going to omit, you'll be pleased to know we're not doing everything in these course notes. We omit section 2.2. So lines 716 to 757. Okay, so these are all out. So you can jump over those. And we're going to go to section 2.3, transitive models. Now, we talked a little bit before about transitive models or transitive sets. We might typically think of a transitive model as being just a collection of sets, right, given to us by some term, W here. And the advantage of transitive collection of sets or transitive sets is they have all the epsilon information about their elements and their elements and so on, because there are no epsilon holes. Right? So in general, right, if just if X epsilon here is transitive, right, then we know that the axiom of extensionality holds. Right, in that transitive set. So we call something like this, or W, we say we call it a transitive model. And we know there are plenty of transitive sets because we defined a transitive closure of any set. It sits inside a transitive set. So there's no shortage of transitive sets. Every set X is a subset of its transitive closure here, so this is transitive. Now, in this case, right, we're thinking of, epsilon is a two-place relation, which is, the membership relation, for example, on W. So for any objects that we might have here, U and V and W, maybe U is a member of V, maybe it's not. But W is correct about its things, which ones are members and which ones aren't. So we say W is a transitive model transitive epsilon model. Just to emphasize the fact that we've got here that the epsilon relation is the binary relation on W. But there are other situations where we have things that are very similar to transitive models. In fact, they might be isomorphic to transitive models. So we may also have structures in our universe, H here with some E relation. So this is a binary relation on H. And it's not necessarily set membership, although it might be, I'm not ruling that out, but it's actually isomorphic to some transitive model like this here. So they might happen to be isomorphic to some W epsilon, where now the binary relation symbol is interpreted as the true epsilon. Here, the binary relation symbol in the language is interpreted as E, whatever that might be. So we'd like to know when this happens, or we'd like to know, right, when I can find, if I've got a model like this, can I find an epsilon interpretation which is isomorphic or isomorphic to it? So if we have an arbitrary HE, when it's isomorphic to a transitive, W epsilon. So I might have some H that sort of looks a bit like this, and then, but maybe on top here, who knows what it's like? It's got, might have epsilon holes in, it might have, look like an ice cream cone with a lot of fluff on top here. What the next lemma does is just give two simple conditions here. So that if this is my H here, I can kind of squash the air out of the froth at the top and actually perhaps make it a nice transitive epsilon model. I can just squeeze this top part here and squeeze that down to so all of this looks like it becomes this over here. And in general, I mean, I could have here some X and some set membership epsilon, which is not transitive. That's an example. So another situation is when we have an X epsilon, which is not transitive. So what the lemma then does is tell us how to transitivize X. So lemma 228, then how to squeeze the air out of the holes, how to transitivize X epsilon. So I'm recycling this diagram here for X epsilon. It might be that part of X is transitive, has no holes in, it's nice and solid down here, but then there may be sets in X up here which are missing elements, which are these holes. And the so-called collapsing lemma that's coming up will tell us how to collapse this to squeeze the air out of the holes. So it's called the Mostovsky-Shepardson collapsing lemma. Right, so this is in the 1950s. This was, it's dated there. Right, there's a very eminent Polish logician, and this is very eminent British logician who actually was at Bristol, had his whole career at Bristol, John Shepardson. So sort of due independently to these two here. And we won't do the proof today because, well, we did Fodor's lemma's proof just now. I think two complicated proofs in a day is maybe too much, but I'll talk about the conditions for this collapsing lemma to work. And in the recorded lecture, I'll actually give the proof, which again will come kind of straight from the notes there. So the first part, so there's a definition to start with. This won't work for any old relation E on some H. Set H here, an arbitrary HE, but we'd like to know if. So there's some conditions on this E here for this to work. And the conditions on E are basically that it should be a little bit epsilon-like. After all, it's supposed to be isomorphic to this. So that means in terms of its E relations, they have to be the same as the epsilon relations on M. So this is going to have to be a bit E-like. And this is what the first definition does, 227. So given a term T and a relation R on T, so we say that R is extensional on T if for any, pick any U and V in T, if U is different from V, well, what does the axiom of extensionality say? If these were sets, there'd have to be something that was epsilon inside U, but not in V, or vice versa. Well, now we're talking about a relation R. So if the relation R is to be like epsilon, there better be something that is R less than U, but not R less than V, or vice versa. Then there is some Z in T here. Now I'll say Z is related to U if and only if it's not related to V. It's not the case that it's related to V. So this actually leaves it a little bit agnostic as to whether this side holds, whether Z is R below U or whether it's R below V. But whatever it is, for the other side, the opposite holds. So if Z is R below U, it's not below V. But if it is below V, it's not below U. So what we're saying is the collection of Z such that Z comes below U is not the same as the collection of Z such that Z comes R below V. It's just another way of writing that, this line here. So this is saying that R looks a little bit like has this extensionality property that epsilon does on transitive sets, right? So then epsilon is extensional on transitive sets. So epsilon as a relation is extensional on transitive T. Right? After all, that's just what this says, right? Where I'm using epsilon in place of R. But if t is not transitive, it needn't be extensional. So if t is not transitive, epsilon need not be extensional on t. And you might say, oh, how's that? I mean, epsilon, surely it's extensional on everything, right? But there might be different things in t. They don't necessarily have members on which they differ. There might be different things in t, but without a member of t which serves to differentiate them. So if that's puzzling, then okay, try and think about that a bit more, and you'll learn something about what being extensional is. Right? And what will the lemma say? So I pick a set in V, and what do? We suppose we've got a relation that is well-founded and extensional. On H. So it's a two-place relation, and like epsilon, it's well-founded and it's extensional. Then the conclusion is there is a unique isomorphism so it's not just an isomorphism, there's only one. And unique, and it's called a collapsing isomorphism. Forgot to say that word there. Pi and a unique M which is transitive with pi going from HR. Here, this is an isomorphism to M epsilon. Right. So in the ice cream cone picture, if the relation here is well-founded and extensional, there's only one choice of transitive set that it's isomorphic to. There's M, and there's only one choice of pi, which is this isomorphism. And we'll see in the proof how to construct pi, and then it'll be clear that we're only going to have one M to do this, right? And there's only going to be one pi. We'll see that pi has to take has to be of a certain kind in order for this to work. The second part of the lemma, right, I could bring the diagram back again here for this, says if I've got part of my H, which I call X in the lemma, if this part of H is already transitive, right, and well, in this picture E, but in the statement of the lemma R, if that is just the same as epsilon on this bit here, it may be something else around here, then actually on this bit, pi is just the identity. Right? I mean, if it's transitive, it's got no epsilon holes to squash out. There's no air to get rid of. And if the relation already just is epsilon on this bit, this is just going to go over to the identity here. And this will end up being an initial segment. All the air squashing takes about place outside of this region here. That's the picture, and that's what clause 2 says. Additionally, what have I got? I've got some X, which is like a subclass of H. And actually, if I look at the relation R, if I restrict that to X cross X, this is just the same as epsilon restricted to X cross X. Right? So on this little bit, R is just epsilon, agnostic as to what it is elsewhere. And X is transitive. If it's already transitive, then pi has no effect on X. It's the identity here. Okay, so there will be more about that next time then in the recorded lecture. So it's a convenient place to stop. Is there anything you want to ask then at this point? Okay. Fine. Everybody happy, I hope? Okay, so let's, I'll stop there then and call it a day. Okay, so do send me questions through for the problems class for tomorrow. Okay, I'll say goodbye.